Hi, today I'll be reviewing AP Chemistry Unit 2, Molecular and Ionic Structure and Properties. So let's get started. So 2.1, Types of Chemical Bonds. So the first type of chemical bond is an ionic bond. So an ionic bond is basically an electrostatic force that holds ions together in an ionic compound. And so here you have LiF. And so the valence electron of the lithium, which is shown over here, is donated to the 7 valence electrons of the F, the fluoride. So the F has a full valence electron shell, and the lithium has a full valence electron shell. And this reaction is shown as Li plus F creates Li plus with that electron gone, plus F minus with that added electron. And so the plus is when the electron is gone, as the electron needs to be gained back for the Li to be its whole self again. And the minus is when you have all the electrons, as you need to give them back. And along with that, there's a way to measure this, which is called lattice energy, which is the energy required to separate 1 mole of a solid ionic compound into gaseous ions. You also have covalent bonds, which are like a bond where 2 electrons are shared by 2 electrons. And you have lone pairs, which are pairs of valence electrons that are not involved in covalent bond formation. So a Lewis structure is basically a representation of covalent bonding in which shared electron pairs are shown either as lines or as pairs of dots between 2 atoms, and lone pairs are shown as dots on individual atoms, such as shown over here. So the octet rule basically states that an atom other than hydrogen tends to form bonds till it is surrounded by 8 valence electrons. So 8 is similar to octet. So continuing with covalent bonds. So bond length is basically the distance between the 2 nuclei of 2 covalent bonds. And a polar covalent bond or a polar bond is when the atoms in a bond spend more time with one atom than another, like with hydrofluoric acid. So the unequal sharing allows for a greater electron density near the F atom than the fluoride atom rather than the H ion. And you can measure this by electronegativity, which is the ability of an atom to attract toward itself the electrons in a chemical bond. And this is used to distinguish a polar bond from a nonpolar bond. So a nonpolar covalent bond is when the electrons are shared equally between the 2 atoms. And a metallic bond is when the electrons are not associated with a single atom, and so they can flow freely across the molecule. This allows for an extremely good transfer of heat and electricity. So 2.2, intermolecular force and potential energy. So chemical bonds. So the attraction between the nucleus of one atom and the electron of another is known as a chemical bond. And so there's a balance between the attraction with protons and electrons and repulsion, protons and protons. So this can be denoted by opposite charges attract and like charges repel. And so you have this picture showing the correlation between internuclear distance and potential energy. And you can see how when there's a strong repulsion at the top of the curve, then the potential energy increases, and so there's the unstable arrangement. And so as it goes on, the H plus starts to separate over time. So along with that, you have the different types of bonds. So you have a single bond, which is when 2 atoms are held by 1 electron pair or 2 electrons. And this bond is like the weakest, and it's an extremely long bond. You have a double bond, which is when 2 atoms are held by 2 electron pairs, 4 electrons. And it's like the middle of the batch, like it's stronger than a single bond, but weaker than a triple bond. And a triple bond is when 2 atoms share 3 pairs of electrons. And this is like the strongest and shortest bond. And you have an ionic bond, which is an interaction with the cation, which is positively charged, and an anion, which is negatively charged. And so you can compare PE diagrams with the blue curve being a single bond. So a single bond is shown with the nucleus being less attracted to the bonding electrons, with a longer bond length and a smaller bond energy, while the double bond, which is the red curve, has the nucleus being much more attracted to the bonding electrons, along with having a shorter bond length and a larger bond energy. 2.3 Structures of ionic solids. So an ionic bond is basically, like I said before, an electrostatic attraction between a cation and an anion. So the structure of an ionic solid has the anion and cation alternating. So why do these compounds conduct electricity? So in order to conduct electricity, you have to have the particles be able to move freely and also be charged. So liquids conduct electricity better than solids. And one sort of tip I have for this subunit is to know your atomic radius and to know like the trends with that, as that will be extremely helpful. So 2.4 Structure of metals and alloys. So you have metallic bonds, which are basically positive metal ions surrounded by a sea of valence electrons. And their properties are that they're extremely good conductors of electricity. They're malleable or bendable or ductile, and they can be pulled. So alloys are basically when you combine two or more metals together, such as brass, copper, and zinc. And there's two types of these: substitutional alloys, where you have atoms of comparable radii and one atom substitutes for another in the lattice, or an interstitial alloy with atoms of a different radii with the smaller atom filling the space of larger atoms. And the alloy is stronger than base metal. One example of this is steel, which is shown over here with the carbon atoms filling the space between the iron atoms. 2.5 Lewis diagrams. So Lewis diagrams are basically the symbol of an element and one dot for each valence electron in an element. So these basically represent chemical substances and show the connectivity between atoms. They also display bond order between atoms and show valence electrons that are not used during bonding. And ergo, basically, they're just a visual representation of everything shown in a molecule in an easy to read format. So let's see the Lewis diagram of water. So H and O are basically the chemical symbols of the atom. And you have dashes, which are used to represent the bonds and also are the same as two electrons. And you could use dots as well in order to do this. And so the dots over here are used to represent valence electrons. So Lewis diagrams of individual atoms. So you can use dots to represent individual atoms, and you can confirm whether a single, double, or triple bond forms by using bond energy. So all atoms except hydrogen or helium end up with 8 electrons, which is the octet rule. And some examples of bonds are shown below, with the hydrogen, fluoride, oxygen with its double bond, nitrogen with its triple bond, BH3, CH4, methane, NH3, H2O, and CF4. So let's try a problem with this. So how to construct Lewis diagrams? So first what you have to do is you have to count and you have to sum up all the valence electrons while adjusting for ions. So it's asking us to construct a Lewis dot diagram for PCl3, which thankfully doesn't have any ions. So it's pretty easy. So what we can see is phosphorus, the charge of phosphorus is 5. So 5. And you also have 7 valence electrons in chlorine. So 7 times 3 equals 5 plus 21 equals 26. You also now, once you got the amount of electrons, you have to determine the central atom and place all the other elements around it and put a single bond. So you can determine what the central atom is just by looking at the formula. And most of the time it's the first atom. So P would be the central atom. And so you have 3 Cls. So you can put one over here, you can put one over here, and you can put one over here. Now I'll just change color for bonds. So let's do, wait, okay. So you then have to put a single bond around all of these. So 1 single bond, 2 single bond, 3 single bond. And then you also have to subtract the electrons used for these bondings. And so for a single bond, the amount of electrons between the phosphorus and the chloride is 2 electrons. So it'll be 26 minus 6, which is 20 electrons. And lastly, what you have to do is you just have to put valence electrons and make sure all of these have 8 unless otherwise known. So then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. We have 18. And now we just need 2 on the top for phosphorus. And just you have to check to make sure all of these have an octet. And if they don't, then you can add extra bonds. So this chlorine has 8, this chlorine has 8, this chlorine has 8, and this phosphorus has 8. So we're good. All drawings. And we have another problem of this sort. So basically, this is one of the more AP style questions. And basically, they'll be giving problems like this a lot. And you can see it in many AP tests. So it's good to try it with these sort of problems as they're a bit more on a wider scale. So let's do blue. So first, what the steps ask us to do is to find the total number of valence electrons. So carbon has 4, so 4 times 2 is 8, plus there's one valence electron for hydrogen, so it's 5, plus there's 6 valence electrons for oxygen times 2 is 12, plus nitrogen has 5 as here. And so you have 10 plus 12 is 22 plus 8 is 30 electrons. And now you just put in single bonds for everything. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now you have to subtract the amount of electrons. So each single bond has 2 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So subtract 30 from 18 is 12. And so you have to add these 12 to the structure. So you can't put it in the hydrogens because the hydrogens are already having their octet of sorts, like a quasi-octet. So you can only add it to the nitrogens and the oxygens. So let's put 2 on top of nitrogen. 1, 2, 10. And then let's put it on the oxygen. So 1, 2, 3, 4, so 6. And then 1, 2, 3, 4, 5, 6. So just now what you have to do is check if all of these have an octet. So hydrogen is good, nitrogen has 8, this hydrogen is good, carbon has 8, these 2 hydrogens are good, and oxygen over here is good, and the hydrogen is good. Oh, but you can see here that there's only 6. So what you can do, while the oxygen has 8 and the carbon has 6, you can remove the valence electrons and you can add a second bond, as that will basically make it 4 electrons. So now you can see that there's 8 electrons for all of them, 8 here, and then 8 here, 8 here. And so you have all the electrons, and now we're good. Okay, so 2.6, resonance structures. Well, resonance structures and formal charge. So formal charge is basically the difference between the valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. And this can be calculated by the total number of valence electrons or the total number of non-bonding electrons subtracted from the 1/2 of the number of bonding electrons. So for neutral molecules, the sum of the charge adds up to 0. For cations, the sum of charges equals positive charges. And for anions, the sum of charges equals negative charges. So for resonance structures, you can use multiple Lewis structures to represent a single molecule. For example, with carbonate. So basically what you have is you have the ability for all the oxygen bonds to be equivalent, even though there's an extra bond. So because you can add like a second bond to either of the carbon oxygen bonds, all of them are equivalent. So this is like a resonance structure. And there's also some exceptions to the octet rule, such as the expanded octet, which can allow for more than 8 electrons to be added. And we can see that later. 2.7, Vesper and bond hybridization. So how do we tell the geometry of molecules? So what you can do is you basically can create a 3-dimensional arrangement of atoms in a molecule. And this theory and this model is called Vesper, or valence shell electron pair repulsion. And it accounts for the geometric arrangements of electron pairs around the central atom in terms of the electrostatic repulsion between the electron pairs. And so negative electrons repel each other due to Coulombic forces, while bonds and lone pairs are negative in nature. And so you have bonds and lone pairs that'll arrange themselves in order to minimize the repulsion. And so you can see this over here with the carbon ion. So as the angles are unequal, the electron domains are closer to each other in some cases than they are with others. So what they do is with Vesper, you have the bond angles being 120 degrees instead of 90 and 180. So all the electron domains are equally apart. So molecular geometry depends on the amount of bonds and lone pairs around the central atom. And this number is called the steric number. So each electron domain is counted equally, such as like a single bond, double bond, or triple bond. And each molecular shape has its own name, which I would truly recommend memorizing or understanding. So this is just like a chart with all the whole table of Vesper stuff. And I'll explain all of the bonds. So there's like a lot of types, but I'll try to go over them as best as I could. So the first type of bond that we have is a linear bond, and that's shown over here. So for a linear bond, the bond angle is 180 degrees. And the hybridization is sp. For a bent molecule, the bond angle is 104.4. Well, I was trying to draw a strip, like a curve, but yeah. So the bond angle is 104.4 and the hybridization is sp2. For a tetrahedral, the bond angle is 109.5, which is shown over here. You could also show it like that. So that's 109.5 degrees. And the hybridization is sp3. For a trigonal pyramidal, the bond angle is 107.3 and the hybridization is sp3 also. So you also have trigonal planar with the bond angle being 120 between all 3 of these. And the hybridization is sp2. And you have trigonal bipyramidal, which the bond angles are 90 and 120. And so this part of the half is 120 degrees, while this is 90. So this part is 9 degrees. And this is 120. Again, and this one's 90 also. So you also have seesaw, which is when the bond angles are 90 and 120 degrees, like shown here, and T-shaped, and bond angles are 90 and 180 degrees. And for seesaw and T-shaped, along with trigonal bipyramidal, the hybridization is sp3d. And all of these are derived from trigonal bipyramidal. So all of these are effectively just different versions of the same thing, as shown over here. And lastly, you have octahedral, which is when the bond angles are are all 90 degrees, such as shown over here, and the hybridization of this is sp3d2, and it has some derivatives such as square planar and square pyramidal. You also have polarity, which is when all molecules have their central atoms surrounded by, when molecules have their central atoms surrounded symmetrically, they're nonpolar. And so all major geometries will produce nonpolar molecules. So the presence of a lone electron pair on the central atom will mean the molecule is polar, and some exceptions are linear and square planar, which basically almost always is nonpolar, and lone pairs can cause polarity. So hybrid orbitals and hybridization. So atomic orbitals only apply to individual atoms. So the sp3 hybridization is when you have 4 electron domains, and it can be either 3 single bonds in a lone pair, or 4 single bonds, 2 single bonds, 2 lone pairs. There's like so much possibilities, but it's basically when you have 4 electron domains. sp2 hybridization is when you have 3 electron domains, and like sp3 can be 2 single bonds, 1 double bond, or etc. And you finally have sp hybridization, and sp has 2 electron domains. So sp are basically when it's linear or bent. So yeah, I guess that's it. So, well, I guess this is it, and I hope it helped you review for the AP test. I guess that's all. I'll be trying to release the Unit 4 video today also, and I hope you all stay safe.